Welcome to lecture 5 on circles. In the previous lecture we had derived formulas for the equation of the tangent and normal to a circle. We had also derived an expression for the distance of the length of the tangent from a point to a circle. So, in this lecture we will take a few problems related to tangents to a circle, just to revise what we had done in the last lecture, and then we will define what is meant by the power of a point with respect to a circle. Thereafter, we are going to study the relation between two circles. To be precise, we are going to derive the expression for the common tangents of any two given circles. So, let us start with solving just two problems. So, here is the first question. It says that a tangent PT is drawn to the circle x square plus y square equals 4 at the point root 3 comma 1. So, a tangent is drawn to the circle at this point. A straight line L perpendicular to the tangent PT is tangent to another circle which is given by this equation, and we are asked what are the possible equations for this straight line L, which happens to be perpendicular to the first tangent, but the straight line L itself is a tangent to some other circle. So, let us try to explain this through figure. So, the first circle was x square plus y square equals 4. So, let us draw the coordinate axis here. So, let us say this is the y axis and this is the x axis. We have the origin here. So, the first circle is x square plus y square equals 4. So, this particular circle has center at the origin and has radius equal to 2. So, the first circle C1 is So, the first circle C1 is going to pass through all these 4 point dots that I have shown, because it has a radius equal to 2. So, it will appear something like this. So, this is our circle C1, and the other circle C2 whose equation is given by x minus 3 whole square plus y square equals 1. So, obviously, this circle has a center at 3 comma 0. So, which is here, and has a radius equal to 1. So, this is the other circle C2. So, as we can see, it is clear that both these circles are going to touch each other at this point, which is 2 comma 0. It is said that a tangent PT is drawn to the first circle at a point P, which is square root of 3 comma 1. So, the point P is square root of 3 comma 1. So, let us see where this point is. So, the y coordinate of this point is 1. So, and the x coordinate is, so it should be this point, because this is the only point. This point is in the first quadrant and has a y coordinate equal to 1. So, y coordinate equal to 1. So, the only point is this. So, this is our P. and the tangent at P to the first circle C1 will appear something like this. So, this is going to be the tangent PT So, this is our so let us say this is T. So, this red line is the tangent PT to the first circle C1, and then it is said that a straight line L perpendicular to PT is a tangent to the this other circle. So, it is just said that the straight line L is perpendicular to PT. So, to find and then it is of course said that it is also a tangent to this other circle. So, how do we really need to find the equation of this tangent? Well, the answer is not really that, because we are just the only information about PT that is getting used is that this straight line L is perpendicular to PT. So, what just matters is the slope of this tangent PT. So, if we look at this tangent PT, the slope of this tangent PT is not very difficult to find, but then it is said that the straight line L is perpendicular to PT. So, when we say that it is perpendicular to PT, what it means is that, let us say O is the origin. Now, we know that this this line segment OP has to be perpendicular to PT. So, because this has to be 90 degrees, this is because of the property of the tangent itself, and then it is they said that the straight line L is also perpendicular to PT. So, what that means is that the straight line L will be basically parallel to this line segment OP. So, the straight line L is parallel to OP. So, therefore, for this straight line L, this is very easy to find the slope now. So, the slope of this straight line L will be simply equal to the slope of OP, which is equal to, so that will be equal to 1 minus 0 divided by square root of 3 minus 0, which is equal to 1 by square root of 3, because this point P is actually square root of 3 comma 1 and O is the origin. So, it is very easy to find the slope, and therefore, the equation of L will be of the type y is equal to mx plus c. So, it will be of the type x multiplied by the slope plus c, where c is a constant. So, this is the equation of the straight line L, and because the question is asking us which of these 4 possibilities is a valid equation for L, such that it is actually this line L has to be a tangent to this circle, to this smaller circle. Now, if this straight line has to be a tangent, what it means is that there is only one point where the straight line must touch the circle C2. So, suppose if there is a point, so suppose that L touches C2 at some point x comma y. So, let us say that L touches C2 at some point x comma y, then it is clear that the coordinates of this point where L and C2 touch each other, the coordinates of this point must satisfy this equation as well as this equation. So, both these equations will have to be satisfied, and therefore, if we try to solve these two equations simultaneously, what we can do is we can replace this y by x by root 3 plus c. So, then we get, so we basically have these two equations which must be satisfied by the coordinates x and y of the point of intersection of the straight line L with the circle C2. So, we simply put this y equal to this in this equation, and we get this equation here. Now, it is said that since L, it is said that L must be a, in the question it is said that L must actually be a tangent to this circle C2. So, if L is a tangent to this circle C2, then there should be only one point of intersection between the straight line L and C2, which means that there should be only one solution of this equation. If you see here, this equation is actually quadratic. This equation is quadratic in x. So, potentially depending on the value of c, there could be more than there could in general there could be two solutions of x, but then the idea is that we should choose this c in such a way that there is only one solution of x here in this equation, or basically both the roots must be equal. So, if we choose such a c, then the corresponding line will basically touch the circle C2 at only one place. So, if we open this equation, what we get is and then if we rearrange the terms, we end up getting this equation here. So, for the roots to be equal, the condition is basically that the discriminant should be 0. So, the discriminant here is going to be 2c by root 3 minus 6 whole square minus 4 times 4 by 3, 16, that is 16 by 3 times 8 plus c square. So, this equation, this quadratic equation has equal roots if and only if this discriminant of the quadratic equation equals 0. And then we can further simplify this equation also. So, we will get so this is the first here term, and then we have and this equation, as we can see, itself is quadratic in C. So, we get if we take all of this on the right hand side, we get 4 c square minus 8 times root 3 plus 8 times root 3 into c plus 20 by 3 equals 0, and then the two values of c are C is equal to minus root 3 plus minus 3 minus 5 by 3 . So, the two values of C are this and if we simplify them further, then these are the two values. So, these are the two values that we get for C, and then let us put these values back into the equation. So, the equation was of L. So, the equation of the straight line L was y equal to x by root 3 plus C. So, for the first case where C is minus 1 by root 3, the equation of the line L becomes x by root 3 minus 1 by root 3, that is x minus root 3 into y equals 1. So, and this matches with the possibility A over here. So, A is correct. Let us see the other possibility where C is minus 5 by root 3. So, if we put it there, if we put C equal to minus 5 by root 3, we get the equation x minus root 3 y equals 5. And this, unfortunately, this equation is not in on any of the 4 options. So, option A is the right choice. Let us take another problem. Now, in this problem it is said that let P q and R s be tangents at the extremities of the diameter P r of a circle of radius r. So, what we have is we have a circle, and P r is one of its diameter, radius of the circle is r, and it is said that, so this is R s. So, both P q and R s are tangents to this circle. It is said that if P s and R q, so this is the straight line P s, and here we have the straight line R q. So, it is said that these 2 points Q and S are such that P s and R q intersect at a point which lies on the, so they intersect here, and Q and S are such that this point of intersection of P s and R q lies on the circumference of the circle. So, if that happens, then what can we say about the diameter 2r of the circle in terms of the lengths P q and R s, because there has to be a relation. So, if we take this understanding onto the other, to the next slide, what we have is, we have a circle like this. Let us say this is the center O, we have a diameter P r, the radius of the circle is r, and then it is said that we have two tangents R s and P q. But it is said that these lengths, so these two are tangents, RS and PQ are tangents to this circle, but then their lengths, the lengths of these two tangents are such that if I connect P to S and if I connect R to Q, then those straight lines drawn in red and green will exactly intersect on a point on the circumference of the circle, which is this point. So, that is why I purposefully I had drawn R, I had drawn this green line to pass through this point and R, because that is what the question is asking, that what is the so how should we choose these 2 points Q and S? So, we are asked to find the expression of the diameter in terms of these lengths P Q and R S, such that these two straight lines which are drawn, one is from the point P of this tangent to the point S of the other tangent, and the other straight line is from the point of contact of this other tangent to the circle, which is point R, to the point Q of the first tangent. So, these two are intersecting at, it is said that one has to choose these lengths in such a manner that these two lines intersect at a point, and that point must be on the circumference. So, that is the important condition, that it must lie on the circumference of the circle. So, and of course, this point of intersection is called X. So, here we will be using to solve this problem, we realize that the most important fact here is that these two lines intersect on a point on the circumference of the circle. So, that is the most important fact that will be useful to us, and because they intersect on a point on the circumference, from high school we know that this angle will be equal to 90 degrees. If this point of intersection of these two lines was not on the circumference of the circle, then this angle might not be 90 degrees. Now, because this is 90, let us say that this angle is theta. Now, because this angle is theta and this is a straight line, so this is also 90 degree. So, if we see this right angle triangle PXQ, then we have theta and 90. So, this angle must be pi by 2 minus theta. Since PQ is a tangent, this angle OPQ is 90, this is 90, and this part of that angle is pi by 2 minus theta. Hence, it follows that this angle must be theta. And therefore, now if we look at this triangle RSP, which is also a right angle triangle, it is right angled at R, its angle RSP is going to be, because this is theta, this will be pi by 2 minus theta. And then just by looking, it is now clear that the three angles of this right angle triangle RPS and the three angles of RPQ are the same, because one angle is 90 degrees, the other is theta, and the third angle is pi by 2 minus theta in both the cases, because for the triangle RPQ this angle is going to be, because this is 90 and this is theta, this angle will obviously be pi by 2 minus theta. And since the three angles of these two triangles are the same, these two triangles are similar. So, I am just drawing these two triangles separately. So, I am first drawing this triangle RPS. So, it is right angled at R, the angle at P is theta, and then I am also drawing RPQ, which is right angled at P. And in RPQ, this angle PQR is theta. Since these two triangles are similar, from the similarity ratios we have that RS divided by RP must be equal to this divided by this, which is RP divided by PQ. And from here it follows that RP square is PQ times RS, and therefore, RP is square root of PQ times RS, but RP is nothing but the diameter 2R. So, this basically shows that the diameter is nothing but the square root of the product of the length of these two tangents. So, and that is basically option A. So, next let us see what is meant by the power of a point with respect to a circle. So, let us consider this circle here, whose center is O, and suppose that we have a point P here, and we define the power of this point P with respect to this circle as the squared length of the tangent from this point to this circle. So, let us say that PT is the tangent, PT is a tangent from this point P to this circle, then the power of a point P with respect to this circle, let us say C, is equal to PT square, the square of this length PT. And then we will also prove a very interesting result, that suppose now we construct any straight line starting from P which cuts this circle at 2 points A and B. So, this could be any straight line. So, any arbitrary straight line. So, let us say this straight line here, and this straight line cuts the circle at points A and B, and then we will show that P A times P B is equal to P T square, and this is the power of this point P. So, the product of these two lengths, so these are the lengths from the point P to the to the 2 points where this straight line has cut the circle. And this is true for any straight line. So, even if I had drawn, let us say, another line like this, and if A and B were like this, then P A times P B would still give me the same value of P T square, because remember, this value P T square only depends on the coordinates of this point P. And then I am claiming that if I draw any straight line from P, so I just drew any arbitrary straight line, then the product of these two lengths between this point P and the points where this arbitrarily drawn straight line cuts the circle. So, if I take the product of those two distances, then it will be equal to the power of this point P with respect to the circle. So, let us prove this fact. So, to prove this, let us first connect these 2 points A and B to the center of the circle O over here, and let us also connect this point P B to this point T, and we will also connect A to A and T. Now, let us say that this angle is theta. Then from high school geometry we know that the angle, if the angle subtended by an arc, the angle subtended by an arc, let us say this arc AB at the center. So, I am talking of this angle, is always twice the angle subtended by the same arc at any point on the circumference. So, if we take this point T, then the angle subtended by this arc AB at this point T on the circumference is theta, and therefore, the angle subtended by the same arc at the center is going to be 2 theta. Similarly, now consider this other arc AT. The angle subtended by this arc AT at this point B on the circumference, let us denote it by phi. Then again from the same result that we used earlier, the angle subtended by this arc AT at the center of the circle is going to be twice this angle, which is 2 phi. And now, if we see, this angle is obviously equal to theta plus phi, because it is the exterior angle of this angle of the triangle BAT. Also, if we look at this triangle BOT, it is an isosceles triangle, because this length and this length are equal to the radius of this circle, and therefore, this and this angle are equal, and they are equal to -90° minus theta plus phi. So, 90° minus theta plus phi. Now, since this PT is a tangent to this circle at this point T, the angle PTO is 90°, and therefore, this angle ATP must be equal to 90° minus theta plus this other angle, which is equal to phi. So, now if we see this triangle APT, this angle is theta plus phi, this angle is phi. Similarly, another triangle is BPT. 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 So, the angle at B is also phi, sorry, let us consider the triangle BTP. BTP, the angle BTP is theta plus phi. So, we can just by looking at these two triangles, we can say that triangle TAP is similar to triangle BTP, because all the three angles are of these two triangles are equal. And since they are similar, from the similarity ratios, we get that AP divided by PT must be equal to PT divided by PB. And then from here it is clear that PT square is PA times PB. So, this proves this statement. So, we will try to give a little example here to illustrate the fact that we had just proved in the previous slide, which was PA into PB is equal to PT square. So, this is the coordinate axis. So, the x and the y axis are shown. We have the origin here, and let us say that we have a circle whose center is here at 5,3. It is just an arbitrary circle, and let us say it has radius 2. So, it is something like this. And let us now consider a point P whose coordinates are 2 minus 2. Then clearly the power of this point P with respect to this circle will be the squared length of the tangent from this point P to this circle. So, this will most likely be the tangent. So, the power of this point P is the square of this length P t. Now, to find this P t is not very difficult. Let us join P with the center of this circle at O. We see that this triangle POT is a right angle triangle, and therefore, PT square plus OT square is equal to OP square from the Pythagoras theorem. Now, clearly the radius of this circle is 2, and therefore, OT square is 4, because OT is a radius of the circle. OP square is, because we know the coordinates of both O and P, OP square is 5 minus 2 whole square plus 3 minus 2 whole square, and this comes out to be 30, 34. And therefore, when we use these two values into this equation, we get PT square equal to 30. So, the power of this point P 2 comma minus 2 with respect to this circle is 30. Now, let us consider some other point, let us say 9 comma 5. So, this is 9 comma 5, and let us join this P and 9 comma 5 by a straight line, and let us say that this straight line obviously cuts the circle at 2 points A and B. Now, we will try to find this length P A and P B. We will take their product and verify whether that product is equal to 30 or not, because that is what we had shown in the previous slide. Now, if we see this straight line over here, then the equation of the straight line is that if there is any point, let us say x comma y on this straight line, then y minus minus 2 divided by x minus 2 must be equal to the slope of this line, which is 5 minus minus 2 divided by 9 minus 2. So, if we simplify this, the equation of this line comes to y equal to x minus 4, y equal to x minus 4. Now, the equation, so now we essentially have to find the coordinates of these 2 points of intersection between this red line and the circle. The equation of this circle is given by this equation. To find these 2 points, the coordinates of these 2 points must satisfy both this straight line equation and this equation of the circle. Now, since y is equal to x minus 4, if we replace this y by x minus 4, we get x minus 5 whole square plus x minus 7 whole square is 4, and we can see that what we have got now is the quadratic equation in x. So, we will get 2 different values of x, which will correspond to the x coordinates of these 2 points of intersection. So, the first value of x that we obviously get is x equal to 5, because we put x equal to 5, this left hand will be equal to, left hand side will compute to be 4. So, one solution is x equal to 5, and when x is equal to 5, the y coordinate should be 1. So, this is one of the points, which is this point A. The other solution to this equation is x equal to 7, because when x equal to 7, this term is 0 and this is 4. When x is 7, then y is 3, and this is the other point of intersection. Now, we can easily find these distances P A and P B. P A is equal to square root of which comes out to be square root of 18 and P B is square root of 3 minus minus 2 whole square plus 7 minus 2 whole square, which comes out to be square root of 50. P A into P B is now square root of 18 times 50, which is equal to 30. So, we see that indeed the product of P A and P B is equal to the power of this point P. So, with that we come to an end to this lecture. In the next lecture, we will start a new topic on the common tangents to two circles. Thank you.